Okay. Yeah, I see the little thing moving just now on Zoom. Do you want me to like go back or anything, or just kind of?
Just continue, I think.
Okay.
I'll check with people to hear you.
Okay, great. So we're still in the process as a community of understanding exactly how all of these binary compact objects were formed. We know that in addition to isolated binary evolution, there's some contribution from dynamical evolution in dense environments, such as globular clusters or maybe the disks of AGN. But in order to kind of understand this full picture, we need to really reduce our uncertainty in the merger rates from each of these different channels. The last piece I'll talk about is the high-mass X-ray binaries. If you don't care about gravitational waves or just massive stars in general, is that high-mass X-ray binaries likely played a pretty big role in cosmic reionization. So past redshifts of about 5, HMXBs dominated in the production of ionizing photons in the universe. So to wrap this up, massive stars are important because they play an important role in galaxies. Their evolution is interesting and complicated, which makes it fun to study. And then also they are progenitors to binary compact object mergers, which are observable with gravitational waves, and they likely played a role in the production of ionizing photons for cosmic reionization. So hopefully I've motivated you all enough about why high-mass X-ray binaries are interesting to study. There are different ways that we can study them. So there's a lot of work that goes on kind of connecting HMXBs to binary stellar evolution and also kind of to their host galaxies and galactic, the influence of the galaxy on the HMXB population and the feedback between the two. So there's been a lot of work connecting the high-mass X-ray binary population in galaxies to global galactic scale properties like star formation rate, metallicity, stellar mass. And a lot of that's done using integrated X-ray emissions, so kind of combining all of the X-rays from HMXBs in a galaxy, looking at the luminosity function and understanding kind of how that scales with those galaxy properties. There's also a lot of work being done with the brightest high-mass X-ray binaries extragalactically or HMXBs in the Milky Way, doing more detailed studies of these systems. And a lot of that work is also done with kind of their accretion physics, different aspects like that. And so I'm going to point out the work I'm going to be presenting today kind of is somewhere in between these two. So in nearby galaxies like M31 and M33, we can see a whole population, but we can also kind of get a bit more detail than we could in those more distant galaxies where we can actually identify the companion stars in these systems and kind of study them in the context of their parent populations. So the real reason why nearby galaxies are such a great place to do this work is because they're close enough that we can actually resolve their stellar populations. So I hope that this will work. I have a little video here showing an animation that will zoom in eventually. So you start off with, you see the Andromeda constellation, and here's the little Andromeda galaxy here. So we're starting with ground-based images, and as we zoom in, we're going to transition to the HST data from the FAT survey, the Panchromatic Hubble Andromeda Treasury that I use in my work studying HMXBs and M31. So you can see as we zoom in, we just keep zooming. And then this is kind of the level of detail that we can resolve in M31. So each of these individual points is a star. In the footprint that Hubble covered in M31 for this survey, we got resolved multi-band photometry for over 100 million individual stars in M31. And this is kind of the level of data that we can use to actually identify which star is associated with these X-ray sources that we're observing with Chandra and with NuSTAR. So because of these resolved stellar populations, they're a really great place to study high-mass X-ray binaries. So this is a mosaic of M31 produced from that HST data from the FAT survey. And not only does the resolved stellar populations data produce so much information about these systems, but compared to Milky Way studies, we can actually see all these HMXBs at the same distance. So in galactic studies, there's often some uncertainty kind of with dust along the line of sight for the exact distance to these systems. And then looking at multiple nearby galaxies allows us to do this work at a range of metallicity and star formation rate intensity. So I'm going to show here a little inset image from HST. I think this is actually from the M33 survey, but showing kind of the rough area that we're looking at when we're trying to identify the companion star for an HMXB. So again, to reiterate, with these resolved stellar populations, we can actually identify and characterize the companion star to the accreting black hole or neutron star. And then we can use information from the nearby stars to determine the ages of the systems or the overall age distribution for the population, and then calculate the HMXB production rates. So I'm going to dig now a bit more into that, into the population demographics that we measure in M31 and M33. So just to give a little summary on these two galaxies, so M31 and M33 are the two nearest large spiral galaxies to the Milky Way. They're at a fairly similar distance to us. And you can see this image on the left. This kind of jagged outline shows the outline of the HST FAT survey. And then in M33, this image is actually a mosaic from the HST data that we have in M33 to kind of show these two galaxies side by side. So in M31, the FAT survey covered like a third of the northern disk of M31, and then M33, the HST survey covered kind of the inner disk of the galaxy. One kind of exciting upcoming, we have incoming HST data on the southern half called FAST. So it's the panchromatic Hubble Andromeda Southern Treasury, I believe. The acronyms are out of control with these surveys, but in a very fun way. So you can see that that'll essentially double the area that we've been able to cover with HST. So M31 and M33 are kind of interesting to do these studies in a very analogous way because of the differences between these two galaxies. So M31 and M33 span a range of star formation rate intensity, which I'm showing on the left. So M33 star formation rate intensity is higher. The star formation rate in the area HST covered in M33 is actually higher than it is in that whole area of M31, although there's about a factor of like 8 or 9 difference in the area. And they also span a range of metallicity. So M33 is known to have a pretty steep metallicity gradient. It doesn't get that low at the radii that we get out to with the HST survey, but it still kind of provides a bit of a comparison point there. And so to talk a little bit about, we need this multi-wavelength coverage, not just the HST data, to study the HMXB populations in these galaxies. So I'm showing on the left M31, on the right M33. These are near UV images of these galaxies, and just showing the outlines of the different surveys that I've been using in my analysis. So the pink is the HST data, cyan is Chandra, and then green are the NuSTAR surveys covering both of these galaxies. So in M31, the HST data that we use is from the panchromatic Hubble Andromeda Treasury, which I'll be referring to by its acronym, FAT. And then the cyan comes from a Chandra survey that was designed to overlap with the FAT survey. So the Chandra FAT survey, and then in green is a NuSTAR legacy survey of the bulgin inner disk of M31. So you can see that there's not kind of full coverage in the Chandra HST footprint from NuSTAR, but we were able to look into the sources that are in that overlapping area. In M33, we're using HST data from the panchromatic Hubble Andromeda Treasury Triangulum Extended Region, which is the FATTER survey. And then we're using Chandra data from CHASE M33, which is a survey that covered pretty much like the whole area of the disk of M33. And there's very recent NuSTAR data covering kind of that central stripe through M33 as well. And so just to recap what we get from these different wavelength surveys. So with the Hubble data, we're able to identify and characterize the companion star candidates in these high mass X-ray binaries and measure their age distributions. Chandra is really kind of the pin that allows us to do this work because we need the high angular resolution to identify the optical counterparts. And then the NuSTAR coverage, where we have it, allows us to start to constrain what type of accreting compact object is in the system. So I'm going to walk you through kind of how do we actually identify these companion stars and what type of analysis are we doing to measure these population demographics. So this is going to be kind of our pet HMXB for the talk. So when I show different plots of the SED or the local star formation history, it's this system. So I'm showing on the left an optical from HST, and then on the right an X-ray image from Chandra. So you can see on the right there is a X-ray point source. So if you're not used to looking at X-ray images, they always look like this. We're collecting individual photons, but we're able to measure this circle represents the 1 sigma error on the Chandra source position. So if we then overplot the X-ray source's position onto the HST data, and we astrometrically align the two sets of imaging, you can see that there's one really bright blue star in that 1 sigma positional error. So we do kind of look through by eye because there's not that many of these X-ray sources, but we kind of use a combination of color and magnitude cuts along with that spatial correlation to identify our best HMXB candidates. So one criteria is that they have to be UV bright because we expect they're massive stars, they're going to be UV bright. So I'm showing you here that same star. So this image is the same one I showed on the left, but now I have added the 3 sigma Chandra positional error. And the left is a single band UV image from HST in the 336W band. And then once we can identify that star, we can pull out its photometry from the HST catalog. And you can see here, I have it plotted on a UV color magnitude diagram and then an optical color magnitude diagram. And its position on both indicates that it's a really strong candidate for being a massive main sequence star. So this would make it a very high quality HMXB companion star candidate. So we do this process. So in M31, we came up with our kind of full sample of HMXB candidates was about 55, but our kind of highest quality, once we go through some quality cuts, is roughly 20 in that area. And then M33 has roughly a similar number of highest quality HMXB candidates. So once we've identified our sample of candidates, how do we actually go about characterizing these stars? So I want to take a second to kind of talk about, well, what are our actual goals? What information about these systems are we trying to draw out? So kind of at the very highest order, we just want a large, clean sample of HMXB candidates. We want something where we could potentially say something statistical about what we're seeing. As you'll see with X-ray binaries, like really large samples, I just mentioned like 20 and 55 are tough just because they are inherently rare objects. But more than a couple. So we want a large, clean sample of HMXB candidates. So I'll talk in just a couple minutes about what types of contaminants we might get in our sample. And how we go about removing those. And then we want to characterize these companion stars. So figure out their spectral types and their physical properties like masses, temperatures, luminosities, radii, etc. We want to determine the ages and the production rate for the HMXBs in these galaxies. And then for the subset that have hard X-ray coverage, we want to constrain the compact object type as well. And the overall goal is to kind of get this detailed characterization of the population and use this to compare against simulated populations that we can generate with binary population synthesis in order to say kind of what differences there may be between our synthetic and our observed populations, and what might the cause of those differences be. So I'm showing here just an overview of our sample in M31 and M33. So the color and shape of the points dictates its most likely spectral type based on SED fitting, which I'll talk about how we determine that in just a second. But I'm just showing kind of the footprint of the surveys again, and then kind of the overall distribution of the HMXBs in these galaxies. So I'm going to show now, so for the M33 sample, once we go about identifying the HMXB companion star candidates, kind of first level, we look at them on color magnitude diagrams to try to say, what type of star are they likely to be. So on the left, we see this optical color magnitude diagram. And then the color and shape of the points just indicate we had kind of several different selection criteria that we went through in order to select our samples. So these kind of blue squares are like our highest quality. They're basically just very clearly massive main sequence stars based on their colors and magnitudes. But we also select some stars that kind of move a little bit further red on the CMD because they could be massive stars that are reddened with dust. And so we want to kind of take them into account, and then we could always weed them out later if they seem to be suspiciously not likely to be massive stars. It's interesting to note that when we look at the optical UV and the UV color magnitude diagrams, they kind of collapse down onto the main sequence. So all of these stars, even the kind of red ones, are selected because they're UV bright. So that's kind of our first order selection for our sample. What we then do is we take this multi-band photometry from HST, from the fat and fatter surveys, and we use SED fitting using the Bayesian extinction and stellar tool, or the BEAST, which essentially uses a combination of stellar models of the photometric bias, which we measure by injecting artificial stars into our images and rerunning them through the photometry pipeline to kind of understand how well we're measuring the photometry, and dust models as well to try to back out the intrinsic properties of those stars based off of their magnitudes in the different HST bands. So showing you for our PET HMXB that I introduced earlier, so this is the SED for this individual star. So the black points indicate its measured brightness in the 4 HST bands that we use here. We have 6 HST bands in our data, so we have 2 near UV, 2 optical, and 2 near IR. In our SED fitting, we don't use the IR bands due to really high levels of crowding in the IR images. So we focus on these 4 optical and UV bands. And the thing to pay attention to here is this blue line. The blue line, which is the full model, including the stellar dust and bias. And so you can see just kind of by eye here, this blue line really cleanly goes through our 4 points. This is a really strong fit for this star's SED. So we run these SED fits on all of our HMXB companion star candidates in both galaxies, and that allows us to place them on an HR diagram. So this is for the M31 sample. The colored regions here indicate the expected ranges for O or B type main sequence or supergiant stars. All of the black diamonds are our HMXB companion star candidates. The size of the point is indicative of its best fit radius, just kind of relative to the other points. And the opacity is its quality in our sample. So after we've kind of evaluated potential contaminants. And then the lines are just showing isochrones of different ages. And I'm going to show the exact same plot for M33 here. So again, showing our sample, the same kind of ideas apply here with the sizes and opacities of the points. So it's cool to be able to do this for our sample of HMXB companion star candidates. I want to talk a little bit now about the opacity of the points. So how do we actually determine our best candidate sample? So the big idea is that we're trying to remove contaminants. So things that might look like HMXBs, they might be X-ray point sources with bright blue like optical counterparts. Sometimes we could see foreground stars that could be X-ray flaring or something like that. They could just happen to be along the line of sight. And then often but one of the harder things to get out are background AGN. So those are galaxies that we're seeing through the disk of M31 and M33, which are hard X-ray sources with bright, like blue UV bright point sources. And so I'm going to talk a bit about how we go about trying to remove those from our sample. So the first thing we do is we try to compare the extinction that we measure in the X-ray spectrum for the sources with the optical dust extinction. We expect that those 2 things should be correlated. And if we have a source for which they're completely uncorrelated, that might mean that it's not actually a source in the disk of M31 or M33. So for example, in M33, we have one really major outlier in this space, and we expect that it's probably a background AGN. The way that we're measuring the AV in M33 is that we're using, we get that out in our SED fitting. And so the SED fitting assumes that it's a star in M33. So if it's not a star in M33, it's going to have some kind of outlandish AV that it has to impose in order to make it have a fit to a star. But then when you compare that to the dust extinction, you are usually getting pretty high hydrogen column densities for those background AGN. We also use information from the SED fits. So kind of, for example, if the SED fits just can't return a quality fit to a massive star, that could mean that this isn't a good HMXB candidate. So that can happen if the SED is flat, which would mean that it's likely to be a background AGN. But we also could see perhaps if it looks like its SED is saying it's actually just a low mass star, that could be a chance superposition. The Chandra hardness ratios, so those are from the X-ray observations, and the hardness ratio is kind of like X-ray colors, which tells us essentially like what fraction of its photons is it emitting at harder versus lower X-ray energies. And we expect that accreting black holes and neutron stars in X-ray binaries should be hard. And so if they have soft Chandra hardness ratios, that might mean that we're looking at a foreground star, or perhaps that we're looking at like a supernova. The X-rays are coming from a supernova remnant that we're not necessarily resolving in our optical imaging. That's more of a thing in M33, which has a lot more supernova remnants because of its high star formation rate intensity. But we were actually able to weed those out in M33 using previous identification of those supernova remnants. We also look at infrared colors. So in the HST data, the IR colors, foreground stars are known to occupy a pretty narrow sequence in IR color space. And so we're able to kind of flag stars that might look to be in that color range as potentially being foreground stars. And then lastly, HMXBs are very young systems, so we kind of expect them to be in areas that are undergoing star formation. So we kind of try to look at whether or not they have local star formation in the last 80 million years, which is kind of the time frame that we're looking on for these massive stars. So I want to emphasize that what we try to do in our analysis is we kind of have a system of flags that we raise for each of these things. So we don't say kind of one strike and you're out for a source, because there could be a real reason that an HMXB might not like fit into one of these criteria. For example, the local star formation within the last 80 million years, like if it got a really massive kick, it might be kind of moving outside of its parent environment. If it has a kind of flat looking SED, it could just be really embedded in dust. So we try to kind of use this. If it raises multiple flags, then it's going to be more suspicious to be something that's not a high mass X-ray binary in one of these galaxies. So I'm going to talk now that we have identified our sample and we're able to kind of narrow it down to our highest quality sample. How do we go about measuring the age distribution and the HMXB production rates? So we use spatially resolved star formation history maps in M31 and M33 to do this analysis. So to measure the spatially resolved recent star formation history in M31 and M33, these were done using the fat and fatter optical photometry. So kind of taking the galaxy and gridding it up into spatial bins. So we use color magnitude diagram fitting, and the focus for these recent star formation histories, we optimize the fits for main sequence stars so that our fits are going to be optimized to recover the recent star formation history. I'm showing on the left here a synthetic color magnitude diagram from the M33 star formation history fitting, where each point is a synthetic star that's been kind of simulated to emulate the fatter photometry that we had and the dust. And you can see that the colors are color-coded, or the points are color-coded by the age of the stars. So you can imagine if you had a single age population, you could figure out what age it was by kind of understanding the pattern it makes on the color magnitude diagram. And if we have a population that's been undergoing several epochs of star formation, you can essentially model how those stars appear on the CMD with multiple single age populations that you can weight by different amounts to kind of recreate what we're actually observing. And the weighting tells you something about what was the star formation rate at those different times in the past. So in M31, I used published maps that were done by Alexia Lewis, and then in M33, I led the analysis to measure the spatially resolved recent star formation history from the fatter data. So I'm showing you, again, a little bit more about what do those spatially resolved recent star formation history maps look like. So this plot here shows each panel is a different time frame. So the upper left is 0 to 25 million years. With this optimization for main sequence stars, we go back to about 630 million years. In M31, there are fits that have been done for the ancient star formation history, which focuses more on the evolved stars, but that is yet to be done in M33, but is underway. So you can see here that we've got this time resolution, and then you can see each of these pixels is an individual region where we measured the star formation history kind of independently of the other regions in the galaxy using color magnitude diagram fitting. So for a given HMXB candidate, we look at it, we call its parent stellar population kind of the population in the kind of pixel where it lives. And these pixels are 100 by 100 parsecs roughly. So we can isolate the star formation history around a specific HMXB candidate. So I'm going to show that here. So this is, again, our pet HMXB that I've been showing previously. So you can see over the last 80 million years that the star formation in that region really kind of only really peaked in that 40 to 50 million year bin. So we can take this star formation rate over time. We could then figure out, well, how much stellar mass formed in each of these time bands. And then from that, back out a probability that a star, looking back 80 million years, we're assuming we're looking at a young star, but kind of what bin is it most likely to have formed in? So we can do that for our whole population of HMXBs and kind of sum up those probability distributions to get an age distribution for the whole population. So for M31, I'm showing here this kind of age population. You can see that there's that highest peak is actually in that 40 to 50 million year bin, which you saw in the previous plot. And it's got this kind of broad peak here where it's elevated. The pink line shows if we do the exact same analysis for an equal number of regions in the star formation history maps, agnostic to whether or not there's an HMXB there, and we can kind of compare. We do that, I think, I don't know, something like 10,000 times or something, and I'm showing kind of the median of that on this diagram. So if we combine this age distribution with the overall star formation history in the area that's covered by both our X-ray and optical surveys, we can then back out an HMXB production rate over time. So how many high mass X-ray binaries are we forming per unit of stellar mass being formed in these galaxies? And that's what I'm showing on the right here now. So you can see that this HMXB production rate in M31 is kind of elevated at this 10 to 50 million year time scale. I've done the same analysis now in M33. So I say it's still a work in progress. So this paper is still in prep. But I'm feeling we've pretty much solidified the sample now. And so you can see this age distribution that we get out for M33. It looks a little bit different. So instead of kind of one peak, it's a more bimodal distribution with a peak in this kind of younger 0 to 10 million year, and then another kind of peak at the 40 to 60 million year bin. And then when we again kind of combine it with the star formation history, we back out an HMXB production rate over time. So you can see M33 has this high HMXB production rate at these young times, and then it also has another peak in that 40 to 50 million year range. So this is actually, this age distribution very much matches. There's been a previous study of the M33 HMXB population using archival HST data that was led in 2018 by Kristen Garofoli, and this actually matches the same age distribution that she measured in her analysis, and we expect that this kind of bimodal distribution is somewhat characteristic of basically each peak is a different formation channel for HMXBs. So you get this 40 to 50 million year peak is kind of correlated with the formation and turn on timescale for BE X-ray binaries. And this other peak here is for more massive binaries, so like supergiant black hole type binaries. Okay, so moving on from the age distribution and production rates, I'm going to talk kind of briefly about the compact object classifications. So how do we actually try to figure out what type of compact objects that we're looking at? So we can constrain the compact object type using the NuSTAR colors and luminosities. So there's a lot going on these plots, but just focus for the beginning on the left plot, which is, so this is a hardness intensity diagram, which is essentially a color magnitude diagram in X-rays. And all of the background points are galactic X-ray binaries for which we know the compact object type and accretion state. So the cyan triangles are ULXs. The circles, actually I think the ULXs maybe are not galactic, but the other points are. So the circles are hard accretion state black holes. The green stars are intermediate accretion state black holes, and the triangles are soft accretion state black holes. So I want to clarify, people always ask about if these are intermediate mass black holes, and no, they're all stellar mass black holes, but different accretion states, which just has to do with whether their emission is being dominated by thermal emission from the disk or like more power law emission from the corona around the accretion disk. And then we have pulsars in purple and lower magnetic field neutron stars in yellow. So essentially, if we have a source of unknown compact object type, where it lies on this diagram could tell us something about what is its likely compact object type. And I want to emphasize, so there's two panels to this. It's really like a three-dimensional space that we're looking at. So the x-axis is the same in both of these plots. And then, so this is the medium soft X-ray color, and then the y-axis on the right-hand plot is the hard medium X-ray color. So we use the location of these sources on this hardness intensity and hardness ratio diagram to figure out what are their most likely compact object types. This work has also been done now in M33 using the new NuSTAR observation, so you can see the points on here. One thing to note, a challenge of doing this type of work at M31 and M33, while they're very nearby galaxies, they're still pretty far away, and we're still getting kind of the amount of counts that we get from these sources is what drives these kind of large error bars. So you can see that it's quite possible that a source will span multiple compact object types on this diagram. So this is kind of like what we can do right now with what we have for this whole population. In the future, I think that a really exciting space for this is to be having kind of more wide field and being able to get kind of more photons in a shorter exposure length for X-ray observations to be able to get more timing analysis, because if you detect X-ray pulsations, that really means that you're looking at a pulsar, and that could kind of make this type of classification easier. So I'm showing kind of how do we then go from these NuSTAR classifications back to what we're looking at with HST. So in M31, for the region of the galaxy that is overlapped by Chandra, Hubble, and NuSTAR, I was able to look at, well, what is the optical counterpart in the HST imaging? So anything that has a point source optical counterpart in this top row, these are the HMXB candidates. So you can see that there's not that many, but those are the number of HMXB candidates we have in that overlapping region in the inner disk. And then we were also able to look at for things that we don't resolve a point source in the HST data. But one great thing about the HST data is because of how high the resolution is, we can identify star clusters, and we can actually pretty easily resolve these background galaxies that we're seeing through the disk of M31. And so we're able to kind of look at trends here. So for example, our HMXBs, it looks like we're kind of having a somewhat flat distribution between the neutron stars, the pulsars or hard state black holes, or the intermediate. There's none of them that have those intermediate accretion state black holes. And then there's some sources that don't have a NuSTAR classification, and that could just be because of how large the error bars are on those sources. And we see a really strong kind of correlation between the neutron stars and the star clusters. So I'm going to talk in these last couple minutes about ongoing and future work that I'm doing to kind of continue and deepen this characterization of the HMXBs in these galaxies. So one thing that I'm very excited about is I have an ongoing Keck observation program to get optical spectroscopy for all of the HMXB companion star candidates that I've been showing you on my HR diagrams today. So we had our first half night in October, and then 3 more half nights coming in November. So that is going to be really important for us to be able to kind of confirm the spectral classifications and like the actual physical properties of these stars. It's also going to be really important for us to make sure that we really weed out any background AGN that might have slipped through our quality cuts, because they're going to be very distinctive when we were able to get their optical spectra. And then for kind of future work, we're going to be able to identify good candidates for follow-up time-resolved spectroscopy. So there's only one HMXB in both of these galaxies that is kind of confirmed, has like a compact object mass that's been measured, M33X7. So this is a really kind of exciting opportunity to really expand that sample, and hopefully if we can get some orbital parameters, we could get some mass constraints on the compact objects in more than just one of these systems. And we expect, based off of the demographics that have been observed in the Magellanic Clouds, that a really large fraction of our companion stars should be BE stars. So those are rapidly rotating B stars with decretion disks around their equator that exhibit really strong hydrogen emission, which we think will also kind of make them good candidates for this time-resolved follow-up spectroscopy. And the other piece that I've been working on for a couple years now is how do we actually compare these observations with theoretical models? So how do we compare them with binary population synthesis models? And I will say I don't have a plot to show here because this is still very much a work in progress. But what we're trying to do is essentially create a synthetic population of HMXBs using the star formation histories in M31 and M33 and say, like, how does that actually compare to what we're observing? So this is a really kind of exciting opportunity for this kind of full population scale work. I've been doing ongoing work using Poseidon, which is a new Python-based population synthesis tool to simulate the M31 HMXB population. So what we're trying to do there is take the population that we simulate, figure out what would it look like in the HST data, so kind of converting it to the HST bands, applying realistic dust extinction onto them, and then kind of putting all of those, the real and the synthetic HMXB companion stars onto CMD and kind of say what can we do. We're kind of pausing a little bit right now on that until we get this optical spectroscopy so that we can really fully make sure that any differences we're seeing are true scientific, not just difference comparing apples and oranges, HMXBs and background AGN. And I'm excited to kind of expand this analysis to the M33 HMXB population as well. And yeah, so I will pause here, and I'm happy so kind of to wrap up, talked a bit about kind of why massive binary stars are important, how high mass X-ray binaries kind of play into that bigger picture, and then work I've been doing to measure the population demographics in M31 and M33, and then looking at the companion star characteristic, age distributions, and HMXB production rates in these galaxies, and what we can start to infer about their compact objects. So thank you so much. I will take questions.
Great. We have plenty of time for questions. People online, if you want to raise your hand, I'll get to you. But we have one here.
Thank you very much. It was super interesting. I wanted to ask you about the age distributions you got and the production rate. Were you able to find a connection with the metallicity, with the galaxies properties?
Yeah, so right now I'm really trying to dig into the comparison between M31 and M33. So I think one of the challenges with the metallicity comparison is that at the inner disk, M33's metallicity isn't so different from M31's that we would expect to see a really massive difference. The big difference in kind of the galaxies then is the star formation rate intensity. So I'm kind of still digging into that now, trying to figure out kind of if the difference in the size of the samples that we see is kind of what we would expect based on their difference in star formation rate. It kind of seems like right about now that the samples are like the best quality samples are fairly similar in size. And then if we look at kind of the breakdown in our inferred spectral types from the SED fitting, that those ratios also seem to be kind of similar. But I have to kind of dig in a little bit more to say something decisive on that.
Any other questions? I just want to ask about the future of NuSTAR. I mean, what's the expected lifetime, and are you expecting to get more data on like M31 from it, or?
Yeah, that's a great question. So NuSTAR just had its 10th birthday in June. It's still going strong though, so I don't think we really foresee an end date in sight on it. I don't know if I can quote the exact like expected lifetime of the mission from when it was launched. So in M31, there is new NuSTAR observations that are kind of in the process now. So when I showed, let me see if I can flip back to, maybe I'll just do this. Yeah, so the NuSTAR data that I've been working on so far is just the inner disk, but we do have actually some other observations that are going to be covering the further out disk. The ones that are in the outer disk are not as deep as the inner disk, but it'll still be, I think, interesting and be able to kind of expand the sample. Because I think it's really interesting to be able to kind of go all the way from like the NuSTAR classification of the compact object to the HST optical counterpart, but it's hard in terms of, you know, how bright these sources are at those really high hard X-ray energies, and that kind of cuts our sample down enough that it can be challenging to get a big sample to say something about. And M33, I don't know of any plans to cover more of the galaxy. I mean, it's got a pretty good strip through. I think like, you know, we could kind of get that lower corner of the HST survey. But yeah, that actually just came out this spring. So it was a deep, I think like 1 megasecond of NuSTAR time on M33.
Great, thank you. Question over here.
Thank you. Hello.
Hi.
So you mentioned the FAST that's coming out, which I didn't know was happening. That's super exciting. Are there plans to do this in the South? Because I imagine in the optical, you know, going from 100 million stars to 200 million stars is cool, but going from like 20 to 40 candidates, in my opinion, is cooler.
Yeah. Yeah, that's a great question. So there is quite a bit of X-ray coverage in M31, but we don't have the same Chandra coverage in the southern half. That is something that we have proposed and we'll probably keep proposing to do. But it does take, this is about, I think, like 7 Chandra pointings, like pretty deep observations. So that is something I would really be interested in kind of doing in the future. And also maybe extending the NuSTAR coverage down into the southern disk as well, I think. Yeah, I think sometimes, you know, the challenge of convincing a tech that like 20 to 40 is really that big of a deal is a challenge sometimes.
Totally. Cool.
All right, any last questions? I'll check on Zoom as well. No. All right, if not, let's thank Margaret again.
Thank you.